Hi everyone, my name is Alex Yang. I'm a PhD student in computer science at Georgia Tech, and today I'll be presenting our paper Lit Forager. As researchers, we all know that reviewing literature is a key part of our work. But with so many new papers coming out all the time, the process can quickly become overwhelming. And having access to more papers doesn't always necessarily mean clearer insights. Sometimes it just makes it harder for us to sort through all the papers, connect ideas, and truly understand the field. So at its core, literature review is a sense-making task. Prior research highlights one powerful idea, which is the concept of cognitive offloading. The more we can externalize our thoughts, the less cognitive burden we carry. And we see this in the tools that we are already using. With Zotero or Mendeley, we compile papers into libraries and organize them into linear lists. AI-powered search engines like Semantic Scholar help us further our thoughts with features like quick summaries. And with tools like Argo Scholar, we can spatially lay out information, form visual clusters, and interact with papers in more dynamic ways. So it turns out that VR can take us one step beyond these traditional tools, because it allows us to think and work in 3 dimensions. Instead of being confined to flat lists or small screens, we can surround ourselves with papers and ideas, arranging them freely in 3D space. Prior work, such as Spaces to Think, shows how effective this can be, with evidence that immersive spaces improve memory and help researchers organize complex information more effectively. Other work, like Documents in Your Hands, demonstrates that directly manipulating papers in AR/VR makes the interaction more tangible and embodied. We also have projects looking to combining modalities, such as gaze, gesture, and voice in VR, to make sense-making tasks not only more convenient, but also more natural. So to understand how immersive systems fit into the real-world sense-making workflow, it helps to take a step back and consider how the process itself has been modeled. One of the most influential frameworks is Pirelli and Card's sense-making model here, which describes analysis as 2 iterative loops. The first loop, foraging, involves seeking information, searching and filtering what's relevant, and extracting it into schemas that can later support higher-level reasoning. Synthesis is the development of a mental model from the schema that we just collected, and fits the evidence that we are gathering. So based on this overview, we can make one key observation, which is that most immersive systems focus heavily on synthesis. It also gives much less support to foraging. And as a result, none of them truly supports the complete end-to-end workflow of sense-making. And that gap is what our work tries to address here. To understand how we can build a better immersive system that incorporates foraging, we need to establish a research pipeline, and that starts with a formative study to understand the core user needs. So we want to know what challenges and goals do researchers face when they're conducting literature reviews. For that, we interview 6 researchers. They're essentially experts from various fields. We ask them how they research, organize, and synthesize literature. We then ran a thematic analysis on their responses. And based on the responses, we condensed the elements of literature reviews into these 3 interrelated dimensions. They told us about common practices, like starting out with seed papers or using citation trails, the data they're looking for, as well as when they find literature reviews to be extra helpful. They've also identified the big pain points, including information overload, difficulty in filtering out the paper, and blind spots when reviewing interdisciplinary literature. And these insights became our design goals: intelligent exploration guidance, flexible spatial organization, and seamless transition between foraging and synthesis. And based on that, we designed the features of Lit Forager. And here's how these goals translates into the features. We start out with a paper network. The node represents a paper. We can hover to browse through the papers, pinch to select and drag a paper to anchor in space. We can also long pinch to show the paper details. We can use the hand menu to explore the paper in depth. Here I'm using intelligent paper summary, keyword extraction, and I can use the voice command to attach notes. We can also expand the paper network by recommendation. Here, I'm using recommendation based on citation links. So the paper that my current paper is citing, we can recommend papers via author relationships. Or we can select multiple papers and recommend papers via thematic similarity. We can also use voice command. We can cluster the papers using different modalities, and these thematic clusters emerge automatically. We can unpin and rearrange the clusters in 3D space, and this reflects our mental model. And beyond that, we can also customize clusters by adding or removing links between the papers. And here's an overview of the graph that we just constructed. So after walking through the core features of LitForager, the next question is, how well do these features actually support researchers in practice? And for that, we ran a user study. We recruited 15 researchers, mostly PhD and master's students, with backgrounds in HCI, visualization, and machine learning. They used the MetaQuest 3 headset with hand tracking and voice input. Their task was to build a related work graph starting from a set of C papers, which mirrors the early stage of real literature review, where you're just starting to explore a new area. Each session lasted about 90 minutes in total, including a tutorial, 3 exploration sessions, and a debrief. This setup gave us both time to observe how they use the system and also to hear their reflections on the experience. So with this study design in place, we wanted to focus on 3 research questions. These questions directly map to the key challenges we had identified earlier: interaction, organization, and relevance. Our first question was, how do users choose between different input modalities, gesture, speech, or hand-based menus, when they're exploring literature in VR? Of course, interaction is just one part of sense-making. Beyond how people issue commands, we were also interested in how they actually externalize their understanding in immersive space. So our second question is, how can users externalize their understanding by organizing, annotating, or clustering papers within the 3D space? Our third research question was, how do users develop and refine their sense of relevance during immersive literature exploration? We wanted to understand the criteria participants use to judge papers, whether based on metadata, recommendations, network cues, or personal goals, and how these criteria shifted over the course of exploration. So for the first research question, we looked at interaction logs based on modality usage. What we wanted to focus on was the modalities that people used during different stage of the user study. What we found was that the head menu became the most common and reliable input source across all tasks. Participants prefer it because it was explicit control and has low error risk, especially when they're requesting recommendations. We also noticed the emergence of power users who lean into a specific modality. Some consistently use bimanual gestures for clustering, while others prefer voice for content analysis. Content analysis is also more commonly used in the early stage of foraging, when users are beginning to read more papers and understanding them. Later, clustering becomes more prominent as the literature graph expands and people are trying to build more clusters and extract patterns from them. We saw 2 clear patterns across the users. Some users were system adhering, relying mostly on the auto-generated clusters with minimum changes, and others were more spatially aware, rearranging clusters to match their own mental models. For instance, one participant described building a better web layout to kind of emphasize the central topics and relationships among the papers. And more importantly, layouts evolve over time. Early in the exploration, spaces were sparse and loosely arranged. By the end, participants had more structured and clustered layouts, reflecting their developed understanding of the papers. Recommendation tools strongly influence the relevance judgments. Every participant used thematic recommendations, and about 2/3 relied on citations and reference trails to find bridging papers. A few also used network cues like centrality or cluster position as heuristics. Over time, strategies evolved. Some participants pivoted between recommendation modes or shifted from being very selective to gathering broadly. Others developed structured workflows as the session progressed. The key takeaway here is that relevance in immersive foraging is fluid. It shifts with personal goals, exploration context, and the cues available in the system. So, looking ahead, we wanted to make our recommendations more personalized and adaptive to user goals. We also want to expand multimodal input beyond just menus, gestures, and voices. For example, adding gaze or adaptive combinations would be nice. Another direction is longitudinal studies. We want to see how LitForger supports real literature reviews over weeks or months, not just in single sessions. And finally, we are excited about enabling collaborative sense making, letting multiple researchers explore literature together in the same workspace. And that's the presentation. Thank you so much. Please check out our paper, and we also have a GitHub page where you can try out LibForger on your own VR system.
Hello everyone, I'm Sung-Won from Northeastern University. I'm a postdoc right now, but when I was submitting this paper, I was a PhD student at Virginia Tech. But first of all, thank you for coming for today. I'll rather go out for eat for dinner if I have this late sessions. But yeah, today I'm about to talk about a paper called Exploring Organizational Strategies in Immersive Computational Notebooks. And I want to open today's talks about introducing our main goal. Main goal is exactly same as our title. We want to explore the organizational strategies, like we want to see how the user will going to organize those digital artifacts in the context of immersive computational notebook. So I think a lot of you guys don't really know what is immersive computational notebook. Immersive computational notebook is a prototype system that we built so that data analysis can perform data analysis tasks with an immersive environment using tools like computational notebook, like Jupyter Notebook, maybe more familiar to you guys, to perform data transformation, data visualization, and some comparison analysis more effectively. And then here's some demo video. This is not really related to our research paper at the ISMAR, but this is just about to show how does it looks like. We first display all the codes in a semicircular layout so that they can interacting with same distance to codes. So we have a graph, data table, and so on. And then we are about to remove those outlier in this graph and deleting from those outlier from the initial data. We can extract those data table and we can interact with data table rather than just sticking with writing codes. We can also explore the data table just scrolling left and right and maybe top to bottom. And we can also delete the column just by grabbing it and throwing it away. We are about to delete the outlier from this data table. But by just looking at the number, it may be really hard to find those outliers. So we can create those data visualization from the data table. Thinking like we are creating a axis, like X and Y axis. So now we have a 2D data visualization. We can create it to 3D by adding one more axis. Now it's pretty easy to find the outlier. We can just grab it and throw it away to delete it. And we can update back to the data table, just grab it and put it back into the data table. And once the data table has been updated, so that we can just put it back into the code to update the code without writing any codes. So now the outlier has been removed, and this is how the immersive computation notebook looks like. Oh, and there are some other cases, and we can make all the notebook window bigger. Let's skip the rest of the part. So one of the biggest benefits of having this immersive computation notebook is about to have intuitive organizations. This was because we were working on this immersive environment, display the codes using this infinite display space, and also by having 3D dimension. On a desktop setup, we need to stick with those top to bottom linear coding structures. But within those immersive computation notebook, we can use it left to right, top to bottom, and even back and forth. We could have those 3D dimension, and this was enabling them to visualize those complex analysis paths more effectively. And it's shown to be supporting better sense making. Here we have an example of the branching structures. But what we found here is that even though there's one branching mechanism, participants are trying to have a lot different type of organizational structures. Some of them were trying to have the curved structures, and some of them sticking with flat structures, and some even have tried to have these grid structures so that a larger number of codes can be fit into the compact sizes. And here comes our main motivation. Now we know that there's a lot of exploration has been done when text-based organizational strategies in immersive environment. But for the coding-based documents, no, we didn't really find there's some exploration of coding-based organizational strategies in the context of immersive environment. And we think this is pretty important because for both text-based and code-based organizational strategies, they're still playing with those spatial positions. If you want to do the side-by-side comparison, we place it in the left and right and try to see, we will try to compare better by just thinking about the position. But in the context of code-based documents, we also try to think of the execution order. Execution order can be very different. But depending on this execution order, the spatial positions are changing, and also organizational strategies can be varied. But we know that organizational strategies are pretty important when we're doing data science tasks. So that's why we try to looking for the organizational strategies in the context of immersive environment. And another question was that, what happens when we increase the number of the codes? When we increase the number of the codes, we may gonna deal with increasing number of the codes and plus execution indicators. So we want to know what happens on their organization strategies when we increase the number of the codes. So this came as our two research questions. We want to know what type of spatial structures and execution orders can be utilized in the context of immersive computation notebooks. We want to know what happens to their organizational strategies when we increase the number of the codes. So to address this research question, we have conducted a user study with 20 participants, and they were all experienced in data science. We conducted with two different conditions. One for simple, we have 10 codes, very simple condition. And then for the complex, we double the amount of the code so that we will try to see what happens when we increase the number of the codes. And the figure on the left bottom is the initial setup. We piled up all the codes so that we are not really affecting their mental model on building their or personalizing their workspace. So that and then we ask them to organize the codes in a way that makes sense to them. And they also need to visualize the execution order by grabbing one of the hole, left to right, top to bottom, just grabbing one of the hole and release it into another hole to visualize those execution indicators. And then the results. Oh, I think the figure is okay. But the results, we found 4 different types of structures. One, full cylindrical structures, 360 degree, and half cylindrical structures, 180 degree. And then the quarter cylindrical, just like less than 90 degree. And for the planar, it was a flat structures. And when we count the number of the participants who preferred, we found that pretty similar to the text-based documents. They were trying to have these half cylindrical structures in the coding-based documents. And when we have a look at the execution order, this was pretty interesting. We found 5 different execution order. One is for the linear, where the execution order doesn't really change, going just to left to right. But for the multi-row and column, they were created different execution order by having different rows or columns. But for the D, linear with branch, they start with the linear, and when they need to do the comparison analysis, they will try to visualize those by having branching mechanism. And for the last one, diverse, was indicating that they were trying to have starting from multi-row, multi-column, and then ended up with having branching mechanism. Like try to have multiple execution order in one structures. And when we count the number of the participants, a lot of participants will try to have linear with branching mechanism. And here comes the important parts. When we try to compare between linear and non-linear analysis, we found that most of the participants, actually almost every participant, will try to visualize those complex analysis path into the non-linear analysis. We think this is pretty important because when we compare between the 2D desktop setups, we found that there's like a 30% more participants will try to have these non-linear setups. And then second research question, we want to have a know what happens on the number of the codes when we increase the number of the codes. So I think it's blurred, but It's pretty visible. So when we increase the number of the codes, for the participant who choose for fully cylindrical structure, like 360-degree, um, in the simple condition, when there's less number of the codes, they could maintain this beautiful circular shape. But when we increase the number of the codes, participants are not able to have this beautiful circular shape. They were actually resulted in spiral shape. But the problem here was that they need to go through the other cells that are placed behind, which was providing not really intuitive interactions. And also including a lot of collusion issues. Increasing number of the codes was also indicating that increasing number of the execution indicators. But to visualize those execution orders in this setups, execution indicator were going over all the other codes. So it was hiding the critical informations. And then when we increase the number of the codes, it was they were experiencing either horizontal or vertical expansion. So that they need to walking in a longer distance, or they need to looking up and down in a wider range. And here comes some interesting findings. When we increase the number of the codes, participants are trying to have some kind of specific space management strategies. Because our initial setup, not all the codes were not visible. So if they wanted to have a better understanding of the codes or fully understanding of the given codes, they need to have those kind of space management strategies. A, presentation space, so that they could tell the answer to us where the position, execution indicators are clearly visualized. But for the scratch space, they use this space to just try to understand the code. They don't really care about the order, execution order, any kind. But they use this B for the scratch space to understand the code better. And when we count the number of the participants who use these strategies, for the simple, almost everyone did it. But for the complex, there's like 30% less, 25% less participants who try to have these space management strategies. So we asked like, why? Why did you not choose for having these strategies? And they said they don't want to do more interactions. Because if they want to do this kind of strategies, they need to moving from initial setup like to have this scratch space, like moving everything one by one. But when we increase the number of the codes, they were hesitating to move their body a lot. But when we count the entire number of these interactions, they interacted with cells position to create their organizations, we found that participants who have these space management strategies were ending up less interactions. So we found that when we increase the number of the codes, participants are either gave up of having nice organizations, or they need to put extensive effort to have those well-organized workspace. And finally, we came up with this 4 type of design implication. First of all, we found that we need to provide half cylindrical structure as an initial setup, same for the code-based documents. And then the second one, we should support nonlinear execution order, but we should avoid collision issues as well. And we can also utilize semantic zoning, and we also need to support low effort interaction for when we need to interacting with large scale analysis. And that's all. I'm very happy to answer any questions. If you're shy, you can scan the code. That's just simply, we found that a lot of participants prefer to have cylindrical structures, not like planar, because we found that we have collected 20 participants, and there are like only 1 or 2 who try to have those planar structures. Mm-hmm. Yeah. Mm-hmm. Oh, I can answer your question by telling this. When we increase the number of the codes, the flat structures we're asking them to moving horizontally a lot. So they may want to avoid those kind of extensive interaction. But while in the semi-cylindrical structure, they can fit more number of the codes so that they can reduce the interactions. So they might be the one of the reason.
Yeah, thank you for the great presentation. And I have one question and one kind of like opinion about it. So the question is, did you measure like how the participants move around depending on the like complexity of the code? So I think it's gonna be, as you mentioned, even if it increases, it seems like people just tend to not move that much. So I think there might be some correlation between the movement area and the length of the code. So the question is like think about measuring that kind of metrics, and the other one is, I think like if you're splitting some screens, many people we just use the preset of it, and I think depending on the length of the code, it might be also related with some recommendation for each the lengths of the code. So what do you think about? Is it like possible to make some functions to manage that lengths and provide some recommendations, something like that?
Yeah, that's a very good question. I wanted to share the DI I mean, design implication for on the right bottom side. That's like how we did. We try to address those scalability when we increase the number of the codes. So we try to have this template interactions, and right now we are about to adding on top of it. We're trying to adding on this AI features to provide some kind of recommendations. That's what we're trying to do, but I can tell you more after this talk.
Great.
Thank you.
Thank you.
Hello everyone, I'm from the Yanshan University. My name is Liu Yapeng, and I'm very happy to have a chance to presentation our work in the ISMAR. And our topic is about the Dockerization of Seamless Core Devices Immersive Active Reading Framework for the digital academic lecture. It's a joint work with my supervisor, Prof. Guo Dongliang, and my colleagues Chen Kai and Yang Fengyi. Dockerization is a framework designed to help the researchers reading academic paper more efficiently across multiple devices in mixed reality environments. On the screen, you can see the several graduate students here using the Dockerization to help their reading the academic paper. And at the bottom right, we show our index server that supports the lecture resource size. And first, I will introduce the motivation behind design the Dockerization. As researchers, we will need to read a larger number of the academic paper to stay informed about the latest developments. This process referred to as active reading. However, when the min text here, when the min text and the context resource didn't show at the same page, such as the finger table, and as users have to constantly switch between the pages, which several disrupt the reading flow. As a result, the information integration and the can you see here? And information layout have become one of the key challenges in the field of active reading. And there are many approaches have made a notable progress in facilitating information integration and the layout for academic reading, either by expanding the space or by introducing a novel interface. However, due to the aim of the research, this solution remains constrained by the need for processing physical devices limitation and applicable to specific media type. In practice, researchers engage in active reading across the wide variety of devices for their completing the challenge of providing constantly support. Consequently, there is still a lack of the seamless, immersive, and cross-device framework that can dynamically adapt the diverse reading context in mixed immersive environment. To bring this gap, we proposed Dockerization. And to assist the user during the reading process, it is essential to get to know what they are current reading. So we design a resource acquisition framework capabilities have able to identify and retrieving the lecture resource. First of all, we use the OCR to detect the title of the paper currently displayed and recognize the title is then sent to the indexing servers, which store the metadata such as the paper title, DOI, and the URL from of the related finger and table. Considering the copyright constraint and the strategy efficiency, our system only preserves the metadata rather than the full text of paper. When matching the record is found, the resource service will return the profile to the user, and if not matched, the spider model will try to fetch the related context from the open resource website. This design allows Dog Vision to operate independently of reading platform, enable user to assign the integrated extension resource without any modification on their original reading environment. And once we get all the context resource, it is essential to find a way to arrange all these resources. Also, due to the research engaging in active reading across the diverse devices, a single fixed layout strategy is not insufficiency to ensure constantly usability and readability. Inspired by the Davis work, we study how resource can be displayed in front of users without any disrupt. We invite 12 experienced graduate students to test the different layout according to the devices. We also modeling the relationship between the screen size and the resource size based on the Stevens work, enabling the Dog Vision to dynamically recommend the appropriate display size of the resource. And to validate our design, we conduct a layout rational experience. Participant was required to two types of layout. One is the self-arranged layout, while the other is Dog Vision layout. After 5 minutes familiarize, they complete two sides of the location text in different layout condition. The research time was recorded to compare to assess the impact of layout on the reading. And here is the result. Apparently, the result shows that the Dog Vision layout is significant, reduce the time needed to location the context resource. And the next part is the Dog Vision evaluation experiment. The experiments consist of 5 parts. Before the formal test, each participant have at least 50 minutes to familiar themselves with the Dog Vision and HoloLens 2. Participants then complete 2 types of reading tasks to simulate a real-world academic reading sense. The finger reading and the citation reading test. During both tests, we record the time taken for each participant to complete their understanding. After complete the reading test, the participants need to fill 2 standard questionnaire. The usability system usability scale and the NASA TLX to evaluate the usability of the workload for both Dog Vision size and the traditional digital reading. Finally, we conduct a 10 minutes simul structure interview to gather the cognitive feedback. The interview focuses on the participant option about the ISMAR layout, usability, and suggestion for the improvement. Here the qualitative evaluation result. As shown in the finger, the participant used the Dog Vision complete both reading tasks significantly faster than those using the baseline digital reading method. All improvement was significant statically. indicates that the documentation efficiently enhance the reading efficiency. And here is the subject evaluation result. According both the desktop and the table condition documentation result a lower score in overall workload, mental demand, and temporal demand. Documentation achieve a significant higher USU score both on the desktop and the table. All these results demonstrate that documentation provides a better usability and greater user satisfaction. And the documentation after caring about the users, the documentation still has some limitation. They think the documentation didn't design the particular specific interaction method for the active reading and still have a hard limitation. They think the HMD holds is too heavy to wear more than 1 hours, and the composition of the participant. We invite all the young people from the school. They got the PhD or the master degree, and the last one is academic workflow. About this section, we will do a better interaction design for the active reading, and maybe using a better HMD for the user to assign them to the active reading and invite different age participants to test the documentation further and try to find a new way to support full academic workflows. And here's a demo of the documentation. all the citation in this presentation, and thank you for your time. Yeah. 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 First of all, for supported the diverse devices, we reference the private word and find some students, and they all have the MR experience, and they arrange this all the resource as they want to mix. But there is a requirement by us. They must make sure that they can location the resource as fast as they can, and in the video, I saw the documentation using in a table, uh, uh, and all the context, all the size of the context resource and the position of the context resource suggested by that experiments. And have you, had I clearly answered your question? Yeah, thank you.
Good afternoon, everyone. I'm Jungmin Ri from KAIST, and I'm delighted to be here today because I will be presenting our paper. This research was conducted in collaboration with my excellent co-authors Hyokjin Jang and Jungmin Ri. So I'm looking forward to sharing our findings on optimizing text presentation in VR. Basically, our study investigates the fundamental challenge of reading text in VR, starting with cognitive load. So text descriptions are crucial in both physical and virtual museums, as they provide context and drive engagement. However, most current VR implementations present text in static blocks that are either too long or too short. It is potentially overwhelming users or fragmenting the information. So we need to find optimal text quantity, because improperly segmented information can significantly make it difficult to read efficiently and retain information. The second major challenge is social distraction. So the presence of other avatars can negatively impact users' focus and information processing, because previous studies show that these passive avatars act as visual distractions that decrease concentration during reading tasks. So to investigate the challenges, we framed our study around two core research questions. First, what is the optimal text segment quantity for reading performance and user experience? Second, how does the presence of other visitors interact with the text segmentation to affect readability? Now let's look at the method to answer this question. To investigate the first core question, we designed 4 experimental conditions as first factor text segment quantity. As you can see, when participant aimed at and triggered at a text panel with a controller, the content was dynamically enlarged and segmented into either 1 to 4 or 8 lines in front of a participant. So our goal was to empirically determine the optimal text segment quantity. And the second factor was the presence of visitors. So we want to see how this social element impact reading performance. So participants were randomly assigned to sessions where the virtual museum was either completely empty or where non-interactive avatar agents were present. So to evaluate the impact of our two factors, we utilized a 4 by 2 within subject factorial design with 31 participants, and the order of these conditions was counterbalanced using a balanced Latin square design to mitigate potential sequence effects. And we corrected both objective performance data and subjective experience data as well. After reading the 5 text passages in each condition, participants took a 10 question while still in VR, and this allowed us to objectively measure their understanding and information retention. And beyond the test score, we carefully analyzed the overall task completion time, which was split into reading and solving time. And finally, to gain insight into the user experience, participants complete a post-session questionnaire on a tablet to access 3 subjective metrics. Let's dive into our findings. So as illustrated in the figure, we found a significant main effect for text segment quantity across all 3 objective metrics: comprehension score, reading time, and solving time. And the results clearly indicate intermediate segmentation, which are 2 and 4 lines, consistently showed the best performance in all aspects. Specifically, the 1 line condition significantly impaired performance, resulting in the lowest comprehension scores and the longest reading and solving times. And this suggests that excessively fragmenting the text causes a heavy cognitive load for integration. So turning now to our subjective measures, the results largely mirror the objective performance data. As you can see in the figure, 2 and 4 line conditions were rated the highest across all metrics as well. And this pattern strongly suggests that segmenting text into just 1 line significantly decreased the user experience. And this is because it resulted in the lowest usability and readability scores alongside the highest perceived cognitive load. So therefore, we can conclude that the intermediate segmentation range is critical for ensuring both reading efficiency and user comfort in VR environment. Even though we found no significant main effect for presence of visitors, our analysis revealed highly significant and critical interaction effects between text segment quantity and visitor presence on solving time. So in the optimal intermediate conditions, the presence of visitors significantly increased problem solving time. And this is that social presence acts as a distractor when the cognitive load from text is manageable. So conversely, in the suboptimal conditions, which are 1 and 8 lines, the presence of visitors unexpectedly decreased the solving time. So basically, shorter reading and solving times indicate better efficiency and performance, because it means the user is processing the information with lower cognitive load, cognitive strain, and higher speed. And thus we see that the effect of social presents is contingent on the difficulty imposed by the text segmentation. I will explain more about this in the discussion part. So in this study, the most significant finding confirms our expectation that there is a definitive optimal text segment quantity for reading in VR. So our objective and subjective results consistently demonstrate that segmenting text into 2 or 4 lines maximizes both reading performance and user comfort. And this means the intermediate segmentation is key to reducing cognitive load and maximizing efficiency. So this finding establishes an empirical guideline for content designer. So both overly fragmented, which is 1 line, and overly dense, which is 8 line presentations should be avoided because they significantly hindered comprehension and increased task time and negatively impacted the perceived workload. So now we turn to the cognitive load theory for explanation. The paradox of the interaction is that the impact of social presence is entirely contingent on the cognitive demands imposed by the text segment quantity. In the optimal conditions, the primary reading task was highly efficient and essentially leaving the user's cognitive capacity available. And this meant the presence of the passive visitors could easily be processed as a social distractor, taxing their working memory primarily during the memory retrieval phase. Conversely, in the suboptimal conditions, the primary task was already extremely demanding due to fragmentation or density. So here, the presence of visitors did not introduce additional distraction. Instead, it may have acted as an altering stimulus or a mild social pressure cue. And this unexpectedly increased participant alertness and motivation to better focus on the difficult task. So this theory helps explain why the visitor effect was not uniform, but rather moderate by the difficulty of text presentation. So we can translate our empirical findings into actionable and evidence-based guidelines for VR developers. So, for example, VR developers may consider allowing non-interactive avatars to remain visible in these highly demanding text conditions. And this approach allows us to leverage the environmental element to actually improve performance. On the other hand, So in conclusion, I would like to summarize our main contributions. So our study successfully identified the optimal text presentation. And second, we provide crucial evidence that VR design must be context sensitive. And finally, we suggest that future work should delve into effect of interactive social distractor. For example, talking avatars, moving avatars. Yeah. So that's it. Thank you for your attention. Yes. I think it depends on the situation, but I assume that the results would be similar with AR. Mm, yeah.
Yeah, do you think this reading in virtual reality has any like, or I guess, do you have any conjecture on the differences between reading in VR versus like naturalistic reading that's on like a 2D space and like not in a headset? Would there be like more regressions or like a different reading rate or anything like that? Do you have any thoughts on it?
Uh, can you repeat
Yeah.
your question?
So, in like natural reading and like just flat
Yeah.
2D, like on a screen, there's like often regressions, like returning to previous words, or reading rate is pretty standardized. Do you think that'd be different in virtual reality compared to on a 2D screen?
I think it's quite different because in this setting, this text passage is optimized from um, from previous study, but I think it should compare to the real world. Yeah.
Okay.